my last video, I ended with the Earth is as much a particle as the particles are in particle physics. And at this point, I feel it's important for me to show you quantum gravity. Really. It's like that. But first, we have to continue on with this explanation. You see, in superstring physics, they mystify it by declaring these strings, these unimaginable things that are outside of your perception, outside of your comprehension. You know, that's the trick, right? I'm going to break it down so it's so simple, it just works for you, right? It's not about superstrings, and they say it's how they vibrate. It is not about that. It is about how the particle moves. See, in a unified field theory, something they fail to point out is that in order for each different field to be created by the mass in the universe, the particles themselves have to move in a different way. Not superstrings have to vibrate in some special mystical way. The particles have to move in a different way. I'll show you. In electronics, you have the right-hand rule. What that means is that the current is traveling in the direction of your thumb on your right hand. The field is spinning in the direction of your fingers. Always, 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 no matter how that wire is positioned, if the electrons are moving this way, the field it produces, the magnetic field, spins this way. It's called the right-hand rule. They have the left-hand rule, which is what drives the worm drive in the Red October movie. You know, the movie about Red October. And what that is when you send a current in the direction of your left, of the thumb in your left hand, the actual particles or ocean material, salt water, will spin in this way and produce propulsion. So here we have an example of the way the particle moves creates the field, and the field creates the way the particle moves. Simple, right? Now, in order to break this down even further, we now have to go into a slightly different area of technology, but let's talk about gravitational waves. They have fancy equipment underground that they've had there for a very long time, lasers and all kinds of things, seeking a gravitational wave. On one of the Mythbuster episodes, they have a device that detects earthquakes by detecting changes in the gravitational field. As a gravitational wave, or an earthquake wave, travels through the ground, matter is displaced away from itself and then back to itself, creating a gravitational wave that is measurable. Yet science hasn't been able to find one ever. But for the purposes of detecting gravity and the Mythbusters, it's sitting right in front of your face. Okay? So, we now have a good example of another place where physics has kind of failed and invention has shown the way. Now, in order to do the next level of this, I have to talk a little bit about the truth about quantum mechanics. Quantum mechanics is this. If you take a proton and you take an electron and you squeeze them together, they become a neutron. If you then allow it to go free, it will then fall apart and become a proton and an electron, or a hydrogen atom. If you take them and squeeze them together and then add a proton, it will not decay. You now have a proton and a neutron, and there will be an electron, and you will have heavy hydrogen. Now, the reason this is important is stuck together, they are not stable, they are not balanced until you add a little bit more nuclear field because it is the nuclear field that forces them apart. What occurs in the quantum world that is so weird and so spooky that they mystify is simple. When that proton and that electron are squeezed together, in that space between them, there's some crazy, crazy crap happening, right? The electrons are traveling around at some god-awful velocity. The proton is spinning at who knows what speed, right? And quite literally, inside that space, the tension from the field, the velocity, and everything involved creates crazy energies. That's quantum mechanics. Okay? The place where weird stuff happens. Right? Now, we actually have examples of quantum gravity right here, right now. And I want to use this as an opportunity to explain to you how a particle moves creates the field configuration. You see, a boulder traveling around in outer space has a particular field of gravity, a particular way that it operates. You start it spinning, and it becomes a gyroscope. This changes the way it behaves in gravity. They actually had to map gravity in order to make smart bombs, because they had to have a map of the gravitational field so that the gyroscopes wouldn't lead the missiles off in the wrong direction. They had to have that map in order to get that smart bomb to its target. And that is because a gyroscope responds to the gravitational field just like metal filings respond to a magnetic field. So we know that the gravitational field is mapped. We know it has variations. But what a lot of people don't know is it's polarized. That gyroscope, as it changes in its as it goes around the Earth, changes where its actual position and aligns with the gravitational field inside of it. And a gyroscope is considered a space-stable element. This is an example of how a particle, the gyroscope, okay, creates the field or responds to the field that it is in. But in order to display quantum gravity or quantum effects in gravity, we could use the rather simple one if there's a place between the moon and the Earth where there's almost zero gravity and they grow crystals there, you know, where gravity pulls on gravity. But that's not quite quantum. That's not weird, right? Now, all of the planets that are spinning out there, all of the objects that are spinning have become planets, and they all behave like gyroscopes, and they all find a plane of existence, right? They all exist on this plane. It's the flat, all of the orbits. You look at the side of our solar system, and it's kind of flat, right? This is how it works. But the quantum effect, which I'm going to use to demonstrate quantum gravity, is actually our tidal forces. Now, if you look at a diagram of how the tide goes, on the side where the moon is, you have really high tide. On the exact opposite side of the Earth, you have high tide. This is quantum effects. This is quantum gravity right here. It's weird. Because, according to relativity, all of the water on the Earth should go to one side. It should all pull this way, and the other side should actually not have a high tide. It should have the lowest tide ever. That's not what happens. What happens is that on the opposite side of the Earth, from the moon, water collects and creates a high tide. Why is that? It is because along this flat plane, along this axis, this point of least resistance, where all of the weight of the sun and all of the other weight of the sun come together and create this flat plane in the ether, this flat plane of field that goes out creates this effect because the water is actually more attracted to the water across this plane. Okay? On the side that the moon is, yes, of course, it's a bigger tide, water collects there. On the other side, it is actually collecting along this plane, and what it's actually doing is making the water more attracted to the water, which is why it then collects to that plane, creating a bubble of water on the other side of the Earth. And the way that this works, or the reason this works, is because every single atom is a space-stable element. It is a gyroscope. It has orbits and spin and all kinds of neat stuff, right? So it aligns with gravity, floats in the gravitational field, adds to the gravitational field, and along this axis actually becomes more attracted to itself. Meaning the field of gravity is actually capable of making the water heavier relative to the water. That is a quantum effect in gravity. Right there. Okay? Now, the way that you have to look at this to a good degree is, as far as like relativity goes and the ether and the mechanics go, is this. If you cut a slit wide enough for a person right through the largest mountain on Earth, and you walked right to the center and you stood there and you weighed yourself on a scale, you would weigh less. Not just a little bit, an actual measurable weight change. Because you have mass above you pulling on you, you have mass to the side of you pulling on you, and you have the Earth mass, and you have all of this to the left and the right and up above. And it's going to pull on you with gravity and make you measurably lighter. The effect that ether provides, other than producing matter, energy, light, and field, is the thing that makes quantum mechanics and relativity finally work together when you put it back. And it's called a vector quantity, where one and another force come together to equal a singular force. And the way that this works is now, if you get on top of the mountain, you weigh what you weigh, right? If you go out into outer space, the entire Earth affects you gravitationally wise, from a distance. That's what ether does. Instead of being affected in outer space as though you were standing in that mountain, or as though there was a mountain on this side of you and a mountain on this side of you, or a continent over here and a continent over there, all of these fields become one field at a distance, affecting you from one direction. That is a vector quantity resultant, and that is one of the properties of ether. Now, as you get out beyond our solar system, the whole system affects you as a whole. If you're in between the planets, the gravity of this planet and the gravity of this planet may affect you differently. This is quantum. And as you get out beyond the gravitational field of the system, it affects you as a whole. You get out beyond the galaxy, it affects you as a whole. One of the properties of ether that is quite literally the solution to all of this quantum and relativity don't get along, right? And that's fantastic. It's important, and it works. Now, in string theory, when you get down to that most basic particle level, and how the particles move and create field and effect becomes very, very important in the next segment of my talk. But I think it's kind of time to recap, possibly, because we actually have a history where the true science was hidden from the world for rich and greedy and powerful people. The entire scientific community had to play along or be destroyed. Tesla's Tesla coil was dead from the beginning and an excuse to destroy his character and his career without people seeing the truth of it. The ether really does exist. The light year doesn't. The age of the universe is wrong, and it is empty space that is accelerating. Quite literally. In just a series of 2 videos, most of the problems that physics is looking for are solved by simply looking at time. Now, I'm not really worried about telling you this because the people at CERN are so far ahead of everybody else. There's not anybody in any way or shape or form that could even begin to compete with them. They're 150 years ahead and have built the most fantastic, complicated experiment in history. Nobody's keeping up, okay? They've got it. Nobody else is even close. So really, it's not that big a deal. But maybe when we start to talk about the science that is missing from the world because of it, it might become a little bit more of a big deal next video.